Thierry Martin, happy to have you.
Hello.
Hello.
Hello, this is Thierry speaking.
Yeah, welcome. This is Kannan Modalia speaking.
Hello. Good afternoon, Kannan.
We are going to wait for 2 minutes. So I thought that during the time, I can talk about some interaction between CNES and ISRO. So we are really happy to have you. So here is the visit of the president CNES when he visited.
Yes.
So this was in 2019.
Yes.
And in fact, there is a virtual exhibition, ISRO and CNES, A Common History, presents glimpses of collaboration between India and France in the 60s and 70s. In fact, you can see Jacques Blumont.
Okay, yes.
And Vikram Sarabhai at 1963.
It's a long time ago.
Long time ago. In fact, I even did a search for, he's the founder of CNES.
Yes, exactly.
And in fact, I was even looking for list of satellites at observation satellites launched by CNES. Not all of them are there because there are other satellites as well. For example, these are Earth observation satellites.
Yes.
And you can see Ariane here, 2013. And let me see, communication satellites, I think there were more. Okay. Yeah, it doesn't give the list of who launched, but there were quite a few.
There is a list in the drop down on the right side.
Here is it, area. You mean communication satellite?
Yes, sir.
In the communication satellite,
there is a list on the right side under communication satellites.
List of communications. Okay. So you can see that as early as 2020, something got launched. 2019, 2018. So 2017, actually lots of satellites, communication satellites were launched by Ariane satellites.
Okay, yes, that's correct.
In fact, this Delta, I think this NASA satellite.
It's an American launcher.
American launcher. This was in 1990. After that, we have had extensive collaboration with CNES.
Yes, currently there are some cooperation. It's on a I know a program on about maritime security. To follow the ships on sea to ensure the security.
Yes.
And it's a new project, and it's a cooperation between India and France. And 2 or 3 years ago, I went to India in Bangalore to work with a startup which is called Team Indus. It was the Google race to the moon. I don't know if you heard about this program. It was a startup in Bangalore, and they participate to this race to the moon. It was a race that was organized by Google, and we at NES we were partner of this startup company. So I went to Bangalore, and we tried. Then there were some guys from ISRO also, then some retired people from ISRO that was helping this startup. And I went to Bangalore, and we had some work together, and I explained them how to use Celestlab and Scilab, and it was an interesting project. But finally, after 2 or 3 years, nobody was ready to go to the moon, and Google decided to stop the race. And so it was there was no winner of this race. But I heard that now this startup company is working with American companies in order to prepare transportation of goods to the station that will orbit around the moon. there's a international program for a future station that will be on an orbit close to the moon. And this company is now working with American companies in order to send cargo to this space station.
Okay.
This was my experience with Indian company.
Okay. So maybe we should, let me give a brief introduction to you.
Yes.
So we are delighted to have Mr. Thierry Martin with us. I met him first time in 2009 in the first ever Scilab user conference workshop in 2009 held in the outskirts of Paris. This was a Scilab Tech Forum. And in fact, I gave the keynote speech on our mission. In fact, there I have proposed Scilab Textbook Companion. Right now, we have 625 books. All their solved problems are available in Scilab. That is about 80,000 problems coded in Scilab, available as open source, all the public all over the world. So during that visit of mine, I met Thierry Martin. He was already a senior manager at CNES, and in fact, I chaired his session. And he went on talking about the toolbox that they created, Celestlab. And at the end of the talk, I asked him a question. You seem to be using Scilab for everything. Don't you use any other software? I still remember that answer. So he was actually showing the trajectory of rocket, of a launch vehicle, how it is going and so on. He said that they never reproduce the entire solution in a new software, but they calculate the missing points and then check whether it falls in the same trajectory. And so that way, for the testing purposes, they do use other software. But I don't think he mentioned MATLAB. They use Scilab extensively, and so they are a great friend. CNE is a great friend of ISRO. We have learned a lot from them, and they have helped us a lot in the past. And hopefully, we can also contribute now. We are delighted to have you, Thierry. Please go ahead.
Okay. Okay. I share my screen.
Yeah.
I'm Thierry Martin, and I'm very happy to share with you my experience of using Scilab for computing space trajectories. Space trajectory, it's orbit. As Kanad said, we are using now Scilab for a long time, more than 10 years. And it's true that we use it daily, and we are quite happy of using this product. And for us, there are many advantages of using Scilab. And I will talk about the way we use Scilab, which is a bit specific, and it's a result of 10 years of experience, and I'm happy to share this experience with you. During my talk, I will give some background, and after I will talk about the problematic of tools for mission design, and I will explain what is mission design in my case. For our purpose, we have developed a powerful library, which is called Celestlab, and I will describe Celestlab, and I will describe also our toolkit, which is called AMS, and if I have the time at the end of the presentation, I will maybe make a small demo. And then I will also talk about futures development, where we plan to use the FOSSI toolbox that is developed here in India in Bombay. So in introduction, I want to say that we are using two kind of language for flight dynamic tools. Flight dynamics, it's orbit in space. Flight dynamic in space, it's the study of the orbits. So for preliminary analysis, with what we call mission design, so it's the first, the early phase of the project, where the things are not really defined. We use a lot Scilab. So we use it for studies. We use it to test algorithm. We use it for prototyping. And as I said, we have developed for this purpose a set of tools and also a library, powerful, which is called Celestlab. We are also using Java, the Java language. This is more for operational software in the control center. For this, two kind of library have been developed. One is called Patrius, which is a basic function of flight dynamics, and one which is a bit high level, which is called Sirius. Patrius, it's open source also, and as you will see in my presentation, we make a lot of links between the Java world and the Scilab world and all other languages. It's for us now. It's a common practice. On the plot of the right, just to illustrate what is the kind of work we do, you have a trajectory from Earth to Mars. It's a typical trajectory where you have the satellite, the probe, which is leaving the Earth. The orbit of the Earth is in blue, and the orbit of the satellite is in black. And we computed the trajectory from Earth orbit to Mars orbit in order to make a rendezvous with Mars. Do you still follow me? It's okay?
Yeah.
Yeah,
Please.
perfect.
Perfect.
Tell me if the sound is not correct or anything. So I will introduce what we call the mission design in our context. Mission design, it's the early phase of a mission where we have a mission team that comes with an idea of mission, and for this idea of mission, first we have to find an orbit for the mission, and we have to develop a satellite which will perform the mission. So during the early phase at CNES, we do it in the concurrent engineering way. So I am in the orbit design team, and I have to interface with all the other specialties like electrical architecture, attitude control. Attitude control, it's the orientation of the satellite, onboard instruments, and typically we have in 1 year we have about 15 to 20 new missions to study. So it means that we have to be very efficient in this exercise. And in order to be efficient, we have developed some specific method that are based on Scilab, and the tools that we have developed are aiming to be very efficient and also very creative. So during this early phase, there are many iterations between the idea of the mission and the studies, the capacity, the capability of the mission. So it's an iterative process that usually takes about 1 year from the early idea to the arrival to design and an architecture that we can present to a board, and after we go to the next phases of the project. So what is a new study? So a new study for us, it can be something completely new and difficult. So in this case, it can take several months to study. We have to develop specific tools, and if we can, we will use some existing tools. In our case, it's a completely recurrent study. It's a study that we have already performed several times. And in this time, we have to reuse all the tools and all the results that are already produced. And it can be anything in between. Sometimes it's just a very quick analysis, just a few questions. And we have to be able to answer very quickly to the questions in order not to lose time on recurrent questions. So the question is what kind of tools, what kind of environment we need for these activities that on one hand can be very innovative, and on the other hand, some others are very recurrent. And we have tried to answer to this question. And the question is, not so. The answer is not so easy because it's a compromise between flexibility. We need to be able to adapt the tool if needed, because when there is a new study, it's not obliged that we have the tools that will answer to the question of the new study. Also, we want to have reliable tools, so we have to ensure the robustness of studies. We have to ensure the quality of our result. The tools must be very efficient. So it means that simple questions must be answered very quickly in order to leave time for to spend more time on the difficult questions. And we also want to have a global consistency between the tools and in order to have a current system. So some time ago, so it's more than 10 years ago, we didn't use Scilab. We had tools that were developed under the unique system. They were most of the time they were compiled in Fortran, and we were using shell scripts also. So this solution that was a bit static. It was working. We were able to produce the result, but it was not flexible because it was, as you can imagine, when you have to modify the Fortran tool with a complete graphic user interface. It's quite heavy, and it's not very flexible. And so if you wanted to use this tool for kind of big analysis, or can I say it's exploring analysis, we were forced to develop shell scripts in order to launch several times these monolithic tools. So it was working, but it was not really efficient. So we have developed now an ecosystem built around Scilab. And why did we choose Scilab? Because we find that the language is adapted to our need. It's very close to maths. It's a very good language for engineers because we are flight dynamics engineers and we are not programming engineers, but we have to develop scripts and programs in order to perform our analysis. And also it's with our ecosystem, anybody now in the team can easily use Scilab and Celestlab and all the ecosystem to do a simple calculation, which is not the case in Java, where the first step in order to use Java is quite high. Also, the Scilab language comes with many functions and libraries that are quite useful. So for many classical tasks like mathematics, statistics, we don't need an external library. Everything is included in Scilab. We have also in Scilab many graphical functions that are needed to produce the result that we want to present to the project. They are in Scilab. They are also available free toolbox that we can get on the Atom website. And if we force ourselves to develop a good program and good script, we're using the vectorization. Then the computing time is not too bad, and sometimes it's comparable to compiled languages. So obviously the vectorization requires some efforts, but we have done it for all the functions of the Celestlab library. Also, when you use Scilab, you can do links with other languages, with C language, Fortran, Java, and in our ecosystem, Scilab has become a glue language that is unifying our platform. Also, Scilab evolved, and we can contribute to the evolution of Scilab. And now we have an interface with Java, with XML. You can even develop some graphic user interface in Scilab. And last but not least, we have a very good relationship with the Scilab team that allow to have a good interaction with Scilab and allow us to propose things and contribute to the improvement of the software. So based on this, we decided that Scilab was a language to be used for studies. But in Scilab, you don't find routines for the space mechanics. So we had to develop our own library, and we have developed two libraries that are called Celestlab and Celestlabix, and I will present them now. So Celestlab, it's a flight dynamics library. It's everything is written in pure Scilab language. It's an open source and free library. It contains probably now more than 200 functions, 300 functions probably, because my slide is now a bit old. In Celestlab, we find the most useful flight dynamic functions that we need for studies. And something which is quite important, we have put a very significant effort on the test of the library. So we have comparison, we have validation test and comparison with other reference product and library, like the products, the libraries from the GPL. So far, it's a library from the International Astronomy Unit, Union, sorry. And we have tested also with the historical library from CNES. And in order to facilitate the use of Celestlab and also to facilitate the start of a new script and new development, we have included in Celestlab many demos, tutorial, and things like this. And if I have the time, I will show you at the end of my presentation some demos, some tutorial, and you will see that with the demos, we are able to answer in a few clicks to a generic question, a recurrent question. And this is very useful for us because we can generate some abacus just like this and answer in a few seconds to recurrent question. So this is important for us because if we are able to answer very quickly to recurrent questions, then it leaves us more time to concentrate on difficult studies. I said that Celestlab is pure Scilab code. So you can use Celestlab on any environment, any environment like Windows, Linux, Mac, without any care. And sometimes we are interfacing with compiled products. It's why we have developed Celestlabix. So Celestlabix, it's an extension of Scilab, and it provides interface to tool and library. So the difference between Celestlab and Celestlabix is that Celestlab is pure Scilab language, and Celestlabix link with other languages like Java, C, and Fortran. So the reason for this extension, it's if we are using other library, sometimes it's efficient in terms of computing time. And since we are using the native code, it's an advantage for the validation. We don't modify the code, and we use it as it is, and we just provide a Scilab interface. So we generate two separate toolbox, Celestlab and Celestlab-X, to keep Celestlab simple. Celestlab, you don't care about the environment. It works on any environment, Windows, Linux, Mac. So the link to the product that are used in Celestlab-X are just here at the bottom of the page. So why do we use other languages? For efficiency reasons, and also to make the existing software available in Scilab. For example, the CNES has developed some years ago a very efficient orbit propagator that is used to propagate the space debris in a very efficient way. So this tool was developed in Stella. And so we want to have it in a Scilab world. So we have developed an interface of Stella, and now in Celestlab-X we can use the Stella propagator. We have also developed an interface for the propagation of the what we call the two-line elements, because these are common tools that are used in the world space community. So we wanted to have these tools available in Celestlab-X and not to modify them. So it's we kept the original tools and just provide the Scilab interface. So using this kind of strategy, we have a few bugs and we have less testing effort because the original library is already validated. So it's now it's a common practice in our team to interface with all languages. So here you have the main topics of Celestlab. Because I will know it. I will not get into detail because it's a bit too specific. It's too much related to our own specialty of orbit design. But you can see that in Celestlab, all the functions are classified in topics, and there are several topics, and there is an overall consistency of Celestlab. Here some example of the product that the illustrations, the demos that we can produce with Celestlab, some orbits, some geoids, and some. You can see also the moon phase on the left here. And if I have time at the end of the presentation, maybe I will show you how to execute these demos. Here you can see all the help page of Celestlab. Every function is well documented with example, reference to the literature, and description of the input and output of the function. And there was a big effort that was dedicated to the documentation of Celestlab. And now Celestlab has become a source of technical information. Here, just an example to see how easy is it to propagate an orbit using Celestlab. Here on the first lines, we get the orbit of the space station, International Space Station. This we can get on the internet. And usually we get the orbit parameters under the format. So it's two lines elements. The orbit is described by two 2 lines of figures. So this so we get this orbit description on the internet, and we use a few functions of Celestlab. The function of Celestlab start with CL to propagate the orbit, and at the end we use just Celestlab functions to plot the orbit, and just an illustration of the how simple is it to use Celestlab for some daily work. So Celestlab is available on the Atom website. So I invite you, even if you don't perform flight dynamics or orbit design, maybe just to check. It's free, and it's funny, and so you can install it on your Scilab system and test it, play a bit with it, and after you can disinstall it if you need more space. Why did we decide to make Celestlab open source? For several reasons. It's a commitment for quality, so it forces us to put an effort on validation, documentation, ergonomics aspects. It's also a way to make things standard. So before when we wanted to exchange, we exchange a few equations and a few ideas on paper, and now using Celestlab we can exchange code scripts and tools and that are working on the several environments. So it makes the exchange much more efficient, and also when I'm teaching flight dynamics, I can ask my students to install Scilab, to load Celestlab, and we can perform some flight dynamics analysis, orbit design analysis using Celestlab. In principle, it makes external contribution possible, but in reality, we didn't have many external contribution, but this is not a problem. Now I will talk about a higher level. Celestlab, it's a library of functions, but we also have a toolkit of a workshop that which is more at application level. So it's this workshop, we call it in French, it's AMS, Analyse de Mission Mécanique Spatiale with Scilab. And I will explain how we and why we developed this workshop. So for our daily work, we need functions to develop new scripts and new code. So this is done using Celestlab, but also we need a reference tool that are fully validated for standard tasks. And as I said in my introduction, we want these tools to be very flexible with several levels of adaptability. So this we have answer to this requirements of flexibility because we can. There is a level of adaptability because at the level of the input data file, which is written in Scilab, we can already make some small modifications, and we have a degree of flexibility at the level of the input data file. And also we have designed the tools so that we can easily make a code modification. So this code modification can be sometimes minor. So for example, we want to modify some plots, the regions of the plots, and in other cases we have to do some deep modification. And in this case, the new code will stay in the user domain. It will not become a new tool. It will be a script that will remain for the user. In our context, we are people that are using Scilab more or less every day. So we consider that graphic user interface it's a drawback for adaptability. So for most of the tools, we don't have a graphic user interface. There are a few exceptions, but for most of them, we don't have a graphic user interface. But we have developed the tool in order to keep some ergonomic requirements. So we have simplified the use of the tool, and we have made sure that the use of the tool, even without a graphic user interface, is secure as possible. And with the IMS toolkit, we offer some functionalities that makes the daily work easier. So we have some functionalities that like saving data, reloading data, running data, that are common to very usual for an application. And we offer this functionality, but it's in a very specific way that I will present you in a few slides and maybe in a demo if I have time. So the philosophy, it's that tools must be generic and simple, and the complexity is at the level of the library. Tools must be adaptable. Adaptations are often needed for specific studies, but they are not always kept for the generic usage. So if we modify the tool at the end, we have to decide whether we kept this modification for the generic usage, or if this tool is just it stays as a script associated with a given project. But we have also some requirements, some basic requirements to have a good structuration and a good design of the tools. This will facilitate the adaptability when needed of the tools. In IMS, so in this workshop, we have also a specific library which is called MS. This one is not public, and in this library we have also interface with other languages, C, Fortran, Java, and as like Celestlab, this library is fully tested. So a tool, it's a kind of a structured Scilab script. And where the input data is dissociated from the main code, and we also the code is structure as a good structure as far as possible. So we have, in order to launch the tools to the applications, we have a launching pad which has been developed on Java. It's a small application in Java. And this small application will allow to select an application, to launch the application, and it provides a menu that offers the main functionalities associated to the application. It will be clearer when if I do a demo of the IMS Java interface. So in IMS, you can find many tools that allow to perform interplanetary analysis, orbit design analysis, visibilities, or all the computations we need to perform on daily work. So this is an example of the input data file. You can see it's Scilab language, and in the input data files, it's allowed to use some functions of Celestlab or MS. You have to see the input data file. It's functional inputs to the application. It's if you see the things this way, it provides some flexibility at the level of the input data. Here you can see how it looks. Java interface, the AMS toolkit. So here you can see that the additional menu for a given application. So I have launched the application. It's in French, so covert, and with this additional menu, I can edit, I can modify the input data, I can generate the graphical, I can save the input data, I can save the result, I can reload the result, I can import data, I can even edit the code of the application if I need to modify the applications. So there are many functions that are available under this form. If I can, I will make a demo. So this is an overview. So we have the Java on the left. You can see the Java navigator that allows to select an application. So you select an application, it launches Scilab, and in Scilab, you can operate the application, and so the application is using Celestlab and sometimes over high-level library. Here's some example of the products, graphical products. So you can see orbit contract on the left, visibility, ground station visibility on the right, and every tool generates some graphical products and also some text files results. For heavy computations, we interface with C software. The core of the computation is performed in C. So here you can see some result of coverage for constellation of satellite over the Europe and USA. Yeah, I will not detail because it's a bit specific. It's energy. It's a level of energy depending on the departure and arrival date of a transfer from Earth to Mars. So this was the case of the Mars Sample Laboratory. It's a GPL mission. We have just to illustrate what we can do with Celestlab. We have performed this abacus and showed the solution that was selected by GPL in terms of launching date and arrival date with the associated energy level that was needed for performing this transfer. So now I will just have a slide to talk about future developments. So we are currently working on several improvements. So we still work on trajectory optimization. Now the old chemical propulsion system are replaced by new propulsion system, which are electrical propulsion system, and they are very efficient. But the problem is that the thrust is quite low, and it requires some specific control law to steer the satellite to the good position. So we had some old tools that were developed some decades, more than 10 years ago. These tools are based on optimal control theory, and they were developed in Fortran. So we have some work to provide a Scilab interface to this tool that gives a good result, but they are based on indirect method, optimal control. And in parallel, we want now to develop new software that will allow to compute the optimal thrust direction and for the given transfer. So we will use, for this, we want to use a direct method of optimization with linear and nonlinear constraints. So we want to develop this tool in Scilab. We have a mock-up that works in MATLAB, but we want this tool to be in our toolkit in Scilab and to interface with all the other products that we have in our toolkit. So we want to develop this tool in Scilab because it's very much more convenient for us to have it in our toolkit. And for this, we need efficient optimization toolbox. When I see efficient, it's a toolbox that allow fine tuning, but also which is good in terms of computing time. So we have looked at what is available in Scilab. In Scilab, there are several optimization toolbox, and FOSSEE appears to be a very comprehensive optimization toolbox that we will try to use for this project. For this product, we use currently the fmincon routine, which is available also in MATLAB, and the first test we have performed make clear that we need a very fine tuning of the parameters of the functions in a way which is similar to the use in MATLAB. There also we have also some work on orbit propagation. So this is more to mission to asteroids or mission to the lunar gateway. And for this purpose, we are using the Patrius libraries, the Java library as a core of the new routine. In conclusion, we have to say that the Scilab ecosystem that was developed has been successfully used at ECNES for more than a decade now for orbit analysis in the frame of advanced projects. That was what I described just before. But we have also used it in an operational context because sometimes in operational context, like the mission, the Rosetta mission, where we are in charge to the landing of the Philae lander, and also we were involved in the Hayabusa 2 mascot lander mission. In this context, where we need, because it's a mission to asteroids and comets, where when we start the mission, we don't know exactly the target, the asteroid or the comet. So there is a quite we need a very high level of flexibility for this mission, and sometimes we have a limited budget. For these two missions, we have used a lot Scilab, and we use it very successfully in this operational context. I stress also that we use Scilab with other languages. As I explained, this allows to use the original code and to improve the computational time. As I said in my introduction, CNES supports Scilab from a long time now, and we try to help for future development, especially developments that will improve the quality of Scilab, that improves the code robustness, improves the test coverage and the bug reports. Also, we want to contribute to the strategic orientation, to the roadmap of Scilab that is shared within the community. And I think in this roadmap, we want to propose things that will improve the overall quality of Scilab, and will propose modern and high quality optimization method that are needed for the current analysis. So this is the end of my presentation. I don't know if I have more time to do a small demo. Canan?
How long can you do it in 5 minutes?
5 minutes, yes.
Okay.
So,
Please.
We launch IMS. So this is a Java interface that allow to access the application. So I can select there are several type of application. So I can select a given application for interplanetary transfer, for example. So I will compute the energy, for example, energy levels for transfer from Earth to Mars. So it's called Créneau. So I select this application. So when I launch my application, it launches Scilab. And if I look at the menu of Scilab, I have here the regular button of Scilab, and I have a new one that shows that Celestlab is installed. And I also some a button that is specific to the application. So the name of my application, it's Créneau, it's a French name. So if I click here, I have access to the Celestlab menu that I will present a bit later. And this is the menu of the application. I can edit the input data of my application. I can execute my application. I can deal with the result. I can save the input data. I can save the result. I can modify the code and also save the modified code. So I will, just for the demo, I will execute the application. So this is a transfer to Earth to Mars, and I produce plots that will give the energy level depending on the departure date and the arrival date. The transfer to Mars is about 6 months. So I will not detail the energy level, but this is the Earth trajectory, the Mars trajectory. I can decide if I'm happy with the result. I can generate the plots under the PNG format. Okay, I generate the plots. Okay, I can edit the input data. So this is the input data of my application. So if I describe the input data, you can see it's a Scilab language, but it's quite for people that know this kind of problem. It's very easy to modify the input data file. So I give the input the start planet, your arrival planet. Here I give the file that gives the position of the planet and the ephemeris of the planet, and after I can define the period where I am looking for a solution. So in the input file, I use some Celestlab function. And I also have some description of the algorithm and the output I want to produce. So if I'm happy with the result and everything, I can save the result in a specific directory. But if I'm not happy and I want to modify the code, I can also edit the code of the application. You can see here the code. And so this is a kind of more advanced use of the functions, but it's sometimes it's very useful to be able to modify easily the code. And I modify the code, and after I can save. Save here the parameter application and result. I can save everything, and I don't want to go into too much detail, but this is the idea. It's to have a toolkit that allow to launch many applications that are quite adaptable. If I need, I can also, I have access to Celestlab. So this is the Celestlab toggle that allow me to use Celestlab. So as I said, Celestlab, everything is described in the help. So here you have the help of Celestlab with a description of Celestlab, and all the functions are described. And you see, this is a transformation of Cartesian coordinate to elliptical coordinate. All the functions are described with some examples and some biography, and so there are something like 300 functions. So I will not detail this too much. Maybe I want to show also that in the introductions, there are many cookbooks that are examples that describe common problem. So for somebody that want to start using Celestlab, it's very interesting to look at these cookbooks. We have some generalities, there are some conventions that are described also in Celestlab. We recall sometimes some flight dynamics basics, like the force model. So we describe the different force we consider for the orbital computation. Like this allows to have a good usage of Celestlab. And to finish, I would just want to show you the demos. So demos are very small application used in Celestlab that sometimes produce useful result, but sometimes they produce things that just show the possibility of Celestlab. For example, the moon aspect tonight in Toulouse for a given date, a given latitude. This is the moon in Toulouse. I don't know what is the longitude of Bombay. You have the coordinate of Bombay? No? Okay.
Yeah.
Just to show, it doesn't matter. So I can also produce some maneuvers, abacus.
So let me put it on chat. Yeah, you can see that here. Somebody has posted.
I cannot see the chat, sorry.
Yeah, it is 19 degree north.
Okay.
And 70 east.
19? 19 north and longitude?
72.
72.
Point
okay.
9 east.
0.9. This is the aspect of the moon tonight in Bombay. You will check. So I think this is the end of my presentation. So I don't know if you have a few questions.
Yeah. Is there any question to Mr. Thierry Martin? Thierry, thanks a lot for the talk. We really enjoyed it. And this is actually very impressive. I think this the coordinate transformation, for example, may be useful in several other domains as well, not just in.
Yes, yeah. For example, if you want to transform a Cartesian coordinate to spherical to elliptic.
It may be useful in robotics. It may be useful in various applications. I think it is not in space dynamics. I think people can use it for several other things.
Yes, that's true. But overall, it's Celestlab. It's a space dynamics library. But, So
go ahead.
You can send me if there's some questions. You can send me the question by mail, and I will be happy to answer them. And I send the PDF of the presentation, so you can share it. You can use it and share it with the community.
Sir,
Yeah, Rupak, go ahead.
Sir, can I take a minute to interact with Martin, sir?
Yeah, please go ahead.
Yeah, good morning, sir.
Good morning. Good.
Yeah. Sir, this is Rupak. We interacted over email for the FOSSEE optimization toolbox.
Yes.
Yeah. So I just wanted to thank you. You have been a great source of inspiration for more than 11 years now. Professor Kannan has been speaking about the usage of Scilab in CNES, and your name has always been put up, and we have always been motivated to use Scilab in India at FOSSEE. And I just wanted to thank you for this great effort and motivating us to use open source software like Scilab. Thank you very much, sir.
Yeah, I'm very happy, and I will be happy to continue with to work with you on the FOSSEE optimization toolbox, because it's a nice product, and we are interested in it, and we want to have a high quality optimization toolbox.
Certainly, sir. We'll do our best, sir.
So we will talk over the internet, and maybe,
yes, sir.
in the short in the coming future about FOSSEE.
Thank you, sir.
So
thank you, Thierry, for this wonderful talk.
There's one question on the chat.
Can it be used for optimization of power in multi-beam satellites?
For power, actually, in Celestlab, you have the routines to compute the geometric configuration of the satellite with respect to the sun. For example, you can compute the direction of the sun with respect to the solar panel. So we stop our work at this level, at the analysis of the geometric configuration, and we give the result to the colleagues that are working on power subsystem. And this is the way we work. But with Celestlab, we analyze the geometric aspect of the power of the satellite.
Okay, thank you, Thierry.
Yeah.
To interact with you in the future as well.
Okay.
Thank
So good luck for the workshop, and I will leave you now.
Thank you. Bye.
Bye.